All right, now we're going to begin talking about light. And in this first slide, we're going to answer the question, what exactly is light? Well, first of all, light is a wave. So some of the things that we discussed in previous chapters about waves will be applicable. You can see here we've got the wavelength of the wave, and it's got a velocity that's moving in this direction. It's also what we call an electromagnetic wave. And what that actually means is that it's got an electrical field and a magnetic field that are perpendicular to each other. Now, we haven't discussed electricity and magnetism, so beyond saying that, we're not going to dwell on that anymore. It does, however, travel at a distinctive speed, which we call the speed of light, which is 3 times 10 to the 8th meters per second. And it travels at this speed in a vacuum. Now, that's important because we saw sound, for example, could not travel in a vacuum. It needed some kind of a medium to be transmitted, whether it be air or water or solid, whatever, but it did require a medium. Not so with light. Light travels through a vacuum, and it travels at this speed. There are a whole spectrum of electromagnetic waves, as is shown in this slide right here. Right here, this is showing some of the various frequencies of electromagnetic waves. And up here, we can see some of the different types of electromagnetic waves. Now, right here in the middle is visible, so this is light. But if you go at a higher frequency, then you can see we run into what's called ultraviolet light, X-rays, which I'm sure you've heard of. Gamma rays are very high frequency electromagnetic waves. These are emitted from radioactive materials. Now, if we go on the lower frequency, we can see infrared. You've perhaps heard of infrared cameras. These are electromagnetic waves. Microwaves, of course, we're all familiar with those, as well as radio waves. Down here, it shows you some of the approximations of the length of the waves. Notice that radio waves are like 1,000 meters long, 10 to the third meters. Microwaves are much smaller. The visible rays, about the size of their wavelengths, are about the size of protozoans. And we get down here to gamma rays, which are very, very small wavelengths, 10 to the minus 12, approximately the size of atomic nuclei. Now, this is the frequency of the waves, and you can see that as the wavelengths of the waves getting smaller and smaller and smaller as we go from radio to gamma rays, the frequency, on the other hand, gets larger and larger and larger and larger. So we get down here to the gamma rays, which has this tiny, tiny wavelength of 10 to the minus 12 meters, but it's got a frequency of 10 to the 20th cycles per second. So we can really see this inverse relationship between the wavelength of the wave and the frequency of the wave. By the way, all of these electromagnetic waves, again, they all travel at the same speed, 3 times 10 to the 8th meters per second in a vacuum. In other materials, they can also be transmitted, but they typically move at lesser velocities. So now we're going to take a look at some of the properties of waves. And one of the properties is reflection. And I think we're all pretty much familiar with reflection. You can stand in front of a mirror, see your image. And that, of course, is caused by the reflection of light. Okay, now, reflection can be explained by something that's called Fermat's least time principle. So what this means is you've got a source of light here, and you've got a second point here. Call this point B, this point A. So if you want the light to go from point A to point B, but it's got to hit the mirror first, this path that the light travels happens to take the least amount of time than any other path. Now you can actually prove that mathematically with a little bit of geometry, but after you do, it all boils down to what's known as the law of reflection. And that is that the angle of incidence equals the angle of reflection. Okay, so let's go back to this diagram. This is the mirror right here. Here is the source of light. This is kind of an imaginary line here that's called a normal that is at a right angle, perpendicular to the mirror itself. So the light, if it comes and it strikes at this angle here, this angle that the light ray makes with the normal is known as the angle of incidence. The law of reflection, which also obeys Fermat's least time principle, says that the angle of reflection is going to be equal to this angle of incidence. So if this were to be 30 degrees, for example, this will also be 30 degrees as the light moves off. Refraction is another common property of light, and refraction is the bending of light when light travels into a medium of different speed. Now, light travels in air just about the same speed as it does in a vacuum, 3 times 10 to the 8th, a little slower, but not much. But it travels a lot slower in water, for example. So the least time principle still applies, and if you take a look at this diagram down here, we've got this object here, which is, not sure what this is, but it's in water, and the person's eye up here. So the light is going to travel from this object to the person's eye. Now, you might think at first glance that it might take the least amount of time to go straight, but that's not the case, and the reason why it's not the case is because if it went straight, then it would be spending a lot of time in the water where the light is going to travel a lot slower. So it travels on a path that looks like this. It travels in the water for a time, and then it bends and travels towards the person's eye, like so. And once again, if you do the calculations, you'll find that traveling this path takes a lesser amount of time than any other path. Now here's another one down here that's a little bit, slightly different path, but it goes to the different position of the person's eye. All right, now, refraction is responsible for many optical illusions. Famous one, of course, is the broken pencil. There'll be pictures of this in the book. But here's one right here. This object, whatever this is actually located here. But to your eye, it appears like it's right here. And the reason why is because your eye tends to follow back the rays of light in a straight line. So it looks as though the object is here, where in fact the object is really here. Maybe you've been in a boat, you look down at the bottom, and if the water is clear, it may actually look shallower than it actually is. Once again, that's refraction is responsible for that illusion. Now you might ask, how does light actually know to take the path of least time? Certainly it can't do the calculations and decide that this is the one that's going to take its the least amount of time. So to try to explain that, I've got here like a mechanical analogy, and they've got some diagrams in the book that actually show this same kind of thing with light. But let's say that you're pushing a lawnmower and you're pushing it at an angle here and it's on the sidewalk. Well, all of a sudden you hit the grass. Now it's a common experience that, if you push the same on the lawnmower is going to travel slower in the grass than it is on the sidewalk. But if you'll notice right here, this left wheel of a lawnmower hits the grass first. So it's traveling slower, whereas the right wheel here is still on the sidewalk and that's traveling faster. Well, if you don't steer it, what's going to happen is the lawnmower is going to tend to shift its direction. Like so. It's going to rotate around here, and it's going to follow this path right here. So this is very analogous to what happens with light rays as it goes from a medium where it goes faster to a medium where it goes slower. Now this diagram over here is just the opposite. Here you've got the lawnmower, it's in the grass, and this wheel, the right wheel, hits the sidewalk first where it's going faster. Here the left wheel is still in the grass where it's going slower, so it's going to tend to rotate around and it's going to bend in this direction right here. So this is typical of light when it goes to a medium where it goes faster to where it goes slower. It tends to bend this way. This is called the normal. We saw that before. So it bends toward the normal when it's going into a medium where it's traveling slower. When light goes to a medium where it's traveling faster, what happens? Well, it bends away from the normal. Now, all materials are assigned a value that's called the index of refraction. And the index of refraction, n here, it's defined as the speed of light in a vacuum divided by the speed of light in a material. Now, the speed of light in a vacuum, we've already said, that's always the same. It's 3 times 10 to the 8th meters per second. The other thing is that the speed of light in the material can never be bigger than that. As a matter of fact, it's probably not going to be equal to that either. It's always going to be smaller. So as a result, the value of n, the index of refraction, is always going to be 1 or larger. It'll be 1 if these two values are equal, but most of the time this is going to be bigger than this, and so as a result, the index of refraction is going to be 1 or larger. Also, the bigger the index of refraction, the slower light travels in the material. In other words, the smaller this value is, that's going to make n bigger. So, a couple of examples. Air has an index of refraction just about 1. And that's because the speed of light in a vacuum divided by the speed of light in the air is just about the same thing. Water, on the other hand, is 1.33. So in other words, when you divide the speed of light in a vacuum by the speed of light in water, you get 1.33. You can see, if you know this, you can figure out actually what the speed of light in the material is. Diamond, light travels very slow in diamond. That's got one of the largest indexes of refraction, 2.41.